me go to the.
Hey, I have a question real quick.
Go ahead.
Can you enable chat real quick just so I can post the group me study group in the chat and then you can turn it back off?
Sure. Let's do it quickly. Go on. Let's do it quickly. Go ahead. All right. All right. Samantha Lynn Tickerhop wants to group.com. So please join her if you want to get together. Yeah, sure. No problem, Samantha. All right. Let's get to the application screen. And you're all there. Share. And let me hide this. And let's go to this one. Now tell me, is it the last slide or not? Or we want a little further? Can you tell me? Is it the last slide we talked about?
That was the last slide.
Thank you. I thought so, but that's okay. All right. So far we talked about how to determine the strong acids, strong bases. So strong bases and what do they? So this is a strong acid basically. We talked about the strong acid and strong bases. So acid dissociate in water, make the anion and the hydronium ion. One hydronium ion monoprotic, two hydronium ion diprotic, three hydronium ion and three hydronium ion triprotic. We talked about, right? And if the concentration of hydronium ion is equal to the concentration of nitric acid, for example, or the acid itself, it's a strong acid. If the concentration of hydronium ion is less than the concentration of individual acid, it's a weak acid. We'll classify. I'll give you the list of weak acids and strong acid very soon. So based on the dissociation, right? And how do you measure the concentration of hydronium ion? Negative log of concentration of H3O positive hydronium ion. Likewise, you can do the same thing with the bases. So bases will dissociate into cation, hydration shell, anion, hydration shell, and if it is one hydroxide ion coming from the base, it's a monobasic. Two hydroxide ion coming from the base, one molecule of base, dibasic. Three molecules of hydroxide ion coming from the base, tribasic. Right? That's basically talked about tribasic.
Excuse me.
Yes.
I just wanted to let you know I'm here. I'm at work and I have bad Wi-Fi, so I couldn't join in at the right time if you call my name.
Hey, don't worry about it. We'll talk later, okay? It's all right. Just take it easy. All right.
Okay,
so now,
thank you.
Yeah, if the concentration of, how to determine the concentration of hydroxide ion? By the negative log of hydroxide ion, pOH. pH and pOH. pOH for the hydroxide ion, right? And if the concentration of hydroxide ion equals the concentration of sodium hydroxide, for example, or the base itself, then it's a strong base. If it is less than the base itself, it's a weak base. So that's basically determined. All right. So you got the and also you have seen it from these two slides. The signature motif for acids is always hydronium ion, H3O positive. I already gave the structure of H3O positive. Signature motif for the bases is OH minus. Remember those two. Okay. Now we'll go to this is a summary basically. So the strength of acids and bases. So acids to the proton dissociate completely in water. That's a strong acid. I just said you, right? And then that give you extremely low pH, and we'll see it. We'll do it very soon. Why? So okay. Dissociate when the acid dissociate partially in water, it's a weaker acid, and it's give the high pH. And I will talk about that part very soon as well. So once again, acids, if they dissociate completely in water, strong acid. Dissociate partially, less than 95% or so. Very similar kind of principle we did for solubility, electrolytes, remember? And that's a weak electrolyte, that's a weak acid. Bases apply the same thing. If the bases dissociate completely in water, then this is strong bases and extremely low high pH, range is greater than 7. If they dissociate partially in water, it's weaker bases, and that's a low pH but greater than 7.0. Now, based upon the pH of a solution, it could be classified into 3 groups. Acidic solutions, when the pH of the solution is less than 7 is acidic solution. If the solution if the pH of a solution is greater than 7, it's a basic solution. And if it is equal to 7, it is basically neutral solution. Can someone give me a name of a neutral solution? Does anyone know a neutral solution that we use routinely every day?
Water.
Yeah. So water basically what water has the pH 7.0 approximate. but no, well, it's a pure water, of course. And what it means by that, that water has same amount of hydroxide ion and same amount of H3O positive. We'll talk about hydronium ion. So once again, how to classify the solution as acidic, neutral, or basic based upon the value 7.0. Why 7.0? That comes right here. So in all cases, and I'll prove it, we'll show you the calculation very soon. In all cases, the pH plus pH is equal to 14. All cases means all solutions. Any solutions you take in the world, universe or anywhere, oh come on, you get the always pH plus pOH is 14. And what's the pH? Negative log of concentration of hydronium ion plus negative log of concentration of hydroxide ion, and that must be equal to 14 always. So therefore, you must remember this equation. Therefore, if you know the pH of a solution, then you can calculate the pOH. So let me ask you a question. If a solution has a pH 7, what's the pOH of the solution? If the solution has a pH 7, what's the pOH of the solution?
7.
14 minus 7, 7. If the pH of a solution, if the pOH of a solution is 3.5, what's the pH?
6.5. Wait. Never mind.
3.5. pOH is 3.5. What's the pH? Yeah?
11.5.
That is correct. And is it a acidic solution or basic solution? Is it acidic solution or basic solution?
Basic.
Basic.
That's embarrassing.
Basic. It's a greater than 7. That's right. That's right. So these are the type of analysis that you should be doing in the test. Okay. So make sure that equation. Now let's get to the how do you get the 14? It's a universal equation. If you go anywhere in the planet, any planet, Mars, Moon, Sun, not Sun, of course, Earth, everywhere is this equation holds. Why? Because if the planet or anywhere you can find the water, two molecules of water will make equation like this. They basically it's a reversal sign. I'm just putting like this way. So it's a reversal sign. They dissociate partially. So you get one molecule of water, this one, lone pair of this will take the proton from this water. So become hydronium ion, H3O positive. Other one will resolve into OH minus. So that's the signature motif for base, signature motif for acid. So water could be amphiprotic compound. Who can tell me why it is amphiprotic compound? Water is amphiprotic. Water is amphiprotic compound or molecule. Why? Why it is amphiprotic? Amphi means dual. Just like it came from amphibians, frog live on a land and water. Water has a dual properties. It could be acid, right? Or it could be base. So that's why it's an amphiprotic molecule. So in the test you can ask, right? I can ask always, why water is amphiprotic molecule? Because water can make hydronium ion and hydroxide ion. In other words, a molecule of water will be acid, another molecule of water will be base. You don't know which one, but they can dissociate into hydronium ion and hydroxide ion. So that's why water is amphiprotic compound. Make sure, all right? Make sure that. Now, since you have someone turn on the phone, turn on your phone with iPhone.
Could
All right?
you,
Yes.
could you
Thank
say that again?
Huh? So water is an amphiprotic compound because it can dissociate into hydronium ion and hydroxide ion. Hydronium ion is a signature motif for acid. Hydroxide ion is a signature motif for base. So water molecule could be acid or a base. It's called amphiprotic. Amphi means dual, protic means proton, proton. So it could be dual properties. Now, since this is equilibrium reaction,
I have a quick
meaning
question.
yes.
Where'd you get the 3.5 from in the 14 minus 3.5?
I gave you this one. I will give you this one. The pOH of a solution is 3.5. pOH of a solution is 3.5. What's the pH? 14 minus 3.5. Whatever the number. I think someone gave me 11.5. Okay. Yeah. So those are the. I'll give you this number. I'll give you one of the two, and then you have to use this equation to get the other. It's very simple. Very simple equation.
Wouldn't it be 10.5 instead of 11.5?
It should be 10.5, right? Right. Well, you have to do the math. I'm going with you. You have to do the maths. Correct. That is correct. Very good. All right, correcting yourself. Very good. Good point. All right. So now you have an equilibrium. Two molecules are reacting, making this. You can make the equilibrium constant. K is equilibrium constant. That is equal concentration, individual concentration of the reactant, the products. That's the product, divided by concentration of the reactants. So parentheses indicate concentration, we talked about. So concentration of, oh wait a minute, concentration of hydronium ion multiplied by concentration of hydroxide ion divided by concentration of H2O square. Why square? Because two molecules are there. All right. So you can solve this equation. So K times concentration of H2 square equals concentration of hydronium ion plus multiplied by concentration of hydroxide ion. You can do that. Simple algebraic equation. K is the equilibrium constant. That's a constant. So is the concentration of water. It's an enormous amount of water there, right? When you put something in there. And therefore it is also constant. So constant, time constant, another constant. And that is called Kw. Kw is the dissociation constant of water. W stands for water. K is the dissociation constant of water, Kw. So Kw equals concentration of hydronium ion multiplied by concentration of hydroxide ion. You can do that, right? Very simple equation. Now, so far we came up with this one. Concentration of hydronium ion multiplied by concentration of hydroxide ion equal Kw. If we take a pure water, and measure the concentration of hydronium ion and measure the hydroxide ion, concentration of hydroxide ion is about 10 to the minus 7 mole in pure water. Very difficult to find. You have to get a distill, several times of distillation of water will remove all those impurities and all those things. And that's basically 10 to the 7, the concentration of hydroxide ion and concentration of hydronium ion. So therefore you can multiply those two, right? So concentration of hydronium ion multiplied by concentration of hydroxide ion equal 10 to the 7 times 10 to the 7 is 10 to the 14, right? Everybody okay? 7 plus 7, 14 minus. Then take the negative log, both sides. So negative log of concentration of hydronium ion multiplied by concentration of hydroxide ion equals negative log of 10 to the minus 14. Now this is log A times B, so log A plus log B. So minus log concentration of hydronium ion plus minus log concentration of hydroxide ion equals minus. So you have a minus 14. That minus 14 will come in the front. Minus times minus 14 log 10. It's a natural log, always base 10. Negative log of concentration of hydronium ion is given as pH. Remember, right? We talked about the definition of pH is negative log of concentration of hydronium ion. So that's a pH. Negative log of hydroxide ion is POH. So pH plus POH equals negative times negative is 14, positive 14 times 1. Log 10 is always 1. So 1 times 14 is 14. So that's the universal equation. For all solutions, you always get pH plus POH is 14. pH plus pH 14. And we did some drilling. If you know the pH of a solution, you get the pOH of a solution. Let's say, for example, I'm going to give, I usually ask the question like this way. The Coca-Cola, Coke. The Coke has a pH 8.3. Is it a acidic solution or basic solution? Number one. Number two, what's the pOH of the solution? So pH of a Coke is 8.3 approximate. And what is the pOH of the solution? Is it acidic solution or basic solution? These are the type of questions you can see that. All right. Now, from this equation that we talked about it, you can also calculate the pH of a solution. Now, I'm going to give an example. Okay, that's a question number 1. This will be there in the test. Some of them like this. What is the pH? What is the pH? Please write down. What is the pH of a solution containing 0.1 molar HCl? What is the pH of a solution containing 0.1 molar HCl solution? Give me it. Who can do it quickly? Let's say in the calculator, in the log function. So question number 1, what is the pH? What is the pH of a solution containing 0.1 molar HCl solution? Who can tell me what's the pH? Yes. Let me give you HCl is a strong acid. HCl is a very strong acid. Yeah. Did you do it or no? Yes. Hello.
Is it
Yeah.
1?
Very good. Excellent. Yeah. Negative. Remember, negative log of concentration of hydronium ion. Remember, right? That's a pH, and that is equal negative log of 0.1. That is correct. This is a strong acid. It will dissociate completely. A log of 0.1 is 1. So if I ask you the question like this way, what is the pOH of 0.1 molar HCl solution? What's the pOH? Equal to pH, right? 1. What's the pOH?
13.
Exactly. Very good. Let's say question number 2. Right here. Question number 2. Calculate the pOH.
Can you explain how you calculated that? Like, what did you plug into the calculator to get that?
So how do you get that one? So basically, you take the negative 0.1 and hit the log. I think you should be able to get 1. It's a negative 0.1 and the log function. Your log calculator should do that. Your calculator should have a log function. So that will do it. Practice some, huh?
How did you do the one for he got the answer of 13 when you said you were talking about OH instead of pH?
So pH is 0.1. So pH is 1. Therefore, pH plus pOH is 14. So pOH equal 14 minus 1 is 13. Yeah. Using that equation, the top one, right? All right. Question number 2. What is the pOH? So pOH. Remember the question, huh? This is the question will be asked. What is the pOH of a solution containing solution of a solution? All right. Of a solution containing 0.25 molar sulfuric acid, H2SO4. Who can calculate for me quickly? So once again, what is the pOH? pOH of a solution containing 0.25 molar sulfuric acid. A solution containing 0.25 molar sulfuric acid. What's the pOH? Who can tell me how will you do it fast? So now, this is the step. Think about it, the molecule. Sulfuric acid, H2SO4, is it acid or a base? H2SO4 is acid or a base, huh?
An acid.
As an acid. So that means you should calculate the pH first. That's the rule. And then what will get the pOH? From the equation. pH plus pH is 14. So first calculate the pH. What's the pH? What's the pH of the
2.5?
No.
It would be the negative log of 0.25.
No. Yeah, you're getting closer. So think about the sulfuric acid.
It would be the negative. It would be the negative log of 0.25 squared.
And
is that right?
Getting closer. Oh, no. One more step. Getting closer though. Yeah, sorry. Getting closer. Come on. Okay. So negative.
Oh, is it just 0.25 times 2?
Who said that? Very good. Exactly. That is right. So negative log of 2 times 0.25. Can you explain to everybody why did you multiply by 0.25?
Because there's 2 hydrogens and it's going to dissociate into 2 H3O pluses. So.
Right here. Very good. So sulfuric acid has a 2 proton. It's a diprotic acid. So therefore, if you have a 0.25 here, 0.25 moles of sulfuric acid, you get 2 times 0.25 moles. Excellent. Very good. That is correct. That's what you should do. And if it is triprotic, you should multiply by 3. And if it's monoprotic, you don't have to multiply by 1. This is the same thing, right? That is correct. Exactly what you just said. Absolutely right. So that's why you have to multiply by 2. Everybody okay with it? You got it? All right. So therefore, now do the negative log of 0.5. And that will give you the pH. Negative log of 2 times 0.25 is 0.5. And you can tell me what it is. What's the pH? Did you get? Come on, give me.
0.3.
Yeah, sounds good. 0.3. Very good. 3, there's some number there, but that's okay. You're fine. You're fine. So what's the pOH then? What's the pOH?
13.69897.
Just if we say 0.3, so just subtract 0.3. So pH will be 13.7. Yeah, that's right. That is correct. That is correct. That is correct. Is okay? Everybody all right? Okay. These are the type of questions will be there in the test. At least 1 or 2, and you must know. So the question from here: what is amphiperiodic? Why water is an amphiperiodic compound? If you know the pH of a solution, how can you calculate the pOH of a solution? You must remember this equation. If you are given 0.1 molar, let's say 0.1 molar nitric acid solution, what's the pOH? And you know what to do it. Nitric acid is a monoprotic. You remember the formula of nitric acid, HNO3. It is 1 proton, monoprotic. So the concentration of acid and concentration of hydronium are exactly the same. If you have a sulfuric acid, it's a diprotic. You have to multiply by 2. If it is phosphoric acid, multiply by 3. But phosphoric acid is a strong acid. So the equation gets a little complicated, and we'll talk about later on. All right, so these are questions will be asked from this slide, okay? Let's move on.
I have a good question.
Yep.
So do you always start with the negative log, depending, even if it's an acid or a base, do you always start with the negative log?
So usually, if it's an acid, so let me give you one basic example. Very good point. Since you asked, let's say if I ask you the question number 3. Yeah, let's do another one. So question number 3 is the pH. What is the pH? Write down, please. Question number 3. What is the pH of 0.1 molar sodium hydroxide, NaOH solution? What is the pH of 0.1 molar sodium hydroxide? Yeah, let's do it. Now, first thing first, what will you do? Think about sodium hydroxide. Is it a base or acid? Sodium hydroxide is a base or acid?
Base.
It's a base. Therefore, base is always determined by pOH, not pH. But we can calculate the pH later on. So what's the pOH then? What's the pOH of sodium hydroxide solution? 0.1 molar. You should know the sodium hydroxide is a strong base. So all those group 1 elements are strong base. Completely. Remember solubility? Tell me what's the pOH then? So pOH of 0.1 molar sodium hydroxide is negative log of, what it is? Yes? What is it?
Would it just be 1?
That is correct. That's a pOH. Then what's the pH then? You already know the answer, right? What's the pH?
13.
Minus 1 is 13. That's correct. That's correct. Now, so similarly, if I ask you another question, I don't have a space here, but let's say another question right here on the top. The pH of, that's a question number 4. And 2 of them will be there from there in the test, okay? I did 2 for the bases, 2 for the acids. pH of 0.25 molar barium hydroxide, BaOH2. Remember, group 2 hydroxides are usually insoluble. Remember solubility chart, but barium hydroxide is a strong base. Barium hydroxide is strong base. I will give you the list very soon. So pH of 0.25 molar barium hydroxide is, what is it? First thing first, consider barium hydroxide is an acid or a base? Is it acid or a base?
It's a base.
It's a base, therefore POH, because signature motif for base is P hydroxide ion, POH. So what's the POH then? What's the POH? Negative log of concentration of hydroxide ion. What's the concentration of hydroxide ion?
Would it be 0.25 times 2?
That is correct. Exactly same like a sulfuric acid. So 2 times 0.25. That is right. Why 0.25 again? Because it has 2 hydroxide ion. It's a strong base. That is correct. And that is equal 0.3. Someone gave me before, right? 0.5, 0.3. So therefore pH will be 13.7. 13.7. All right. Very good. So this is the way you can calculate the pH and POH. All right. So, so first thing first, it is not a typo. Many people think it's a typo if you ask the POH of acidic solution, because you can calculate. First thing first, you remember it's an acid, and if it is so, calculate the pH. Once you're done with the pH, then subtract the 14, because pH plus POH is 14. You get the number. All right, we'll move on. So these are questions will be entertained. There are many questions to be asked from this slide, and we already talked about quite a few of those. And get ready for it, okay? Everybody. All right. So now the strength of acids and bases. Strength of acids and bases, as we said completely, right? One that react completely or almost completely with the water to form the hydronium ion. We talked about the strong acid. Strong base is one that react completely or almost completely with the water to form the hydroxide ion. We talked about this one before. Here is the list of strong acids and strong bases, a partial list. There are many others, but you must remember this. You have to read it again and again of this slide to understand this. What are the strong acid? A list. Hydrochloric acid, hydrobromic acid, hydroiodic acid, not hydrofluoric acid though, HF, hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid. They're all strong acids and they're all monoprotic. Why monoprotic? One proton, one proton, one proton, one proton. The ones after dissociate in water, right? So they're all strong acids, all strong acids. Sulfuric acid is a diprotic. It's also a strong acid. Perchloric acid is very strong acid. It is a monoprotic. It's at only one proton. One proton monoprotic, two proton diprotic. Sulfuric acid is a diprotic. All right, these are all strong acid, list of strong acid. So you must remember this, okay? Now, if you mix nitric acid and phosphoric acid together, nitric acid and sulfuric acid together, it gives more stronger, more stronger. In principle, if you take some nitric acid, don't do it, of course. If you take a somewhat nitric acid and mix with the phosphoric acid and just put a drop of in your hand, it will make a hole to the other side. It will go to all the way pass it to the other side. It is so strong. Very, very strong. Sulfuric acid and nitric acid mixture. These two acids are itself, they are very strong acids. HCl is a strong acid. And our stomach has plenty of it, right? Everybody knows, right? Stomach has plenty of it. Once you eat something, this HCl is required to digest the food. So the hydrolysis, called acid hydrolysis. So these are the list of strong acids. And you must remember those, okay? I usually don't give that. Therefore, you must remember in the test. So I can ask the question like a 0.25 molar perchloric acid, what's the POH of 0.25 molar perchloric acid? So you have to know perchloric acid is strong acid, therefore it will dissociate completely. Concentration of hydronium ion is equal to the concentration of perchloric acid, and it is a monoprotic because it has one proton. So you must know the formula, you must know that it is strong acid, and you must know the principle, basic principle, strong acid dissociate completely. Therefore, concentration of acid is equal to the concentration of proton or hydronium ion. Therefore, you can use that concentration to determine the pH. And what's the pH? pH is the negative log of concentration of hydronium ion. Once you know the pH, then you can calculate the POH. So all those concepts are basically digesting together to understand that question. So this is very, very important. One question suffices to indicate your knowledge of all those things that you are digesting with. Okay. Likewise, strong bases, lithium hydroxide is a group 1, most of group 1. Sodium hydroxide, potassium hydroxide, all group 1 hydroxides are very strong bases. Hydroxide, right? Basic. Barium hydroxide is a group 2, not the calcium hydroxide, strontium hydroxide, magnesium hydroxide, they are weak. As you remember, the solubility of those group 2 hydroxides are usually insoluble. They solve very sparingly, dissociate very, very partially, maybe 0.1%, 0.2%, something like that. Barium hydroxide, on contrast, is dissociate completely. It's 100% dissociation. It's a strong base. It's a strong base. So you must remember this list, okay? All right. Let's move on to the next. So acids that we define, acids and bases, those are Arrhenius acids. Arrhenius definition of acids and bases. There is another definition of acids and bases called conjugate. Yes. Yes. Yeah. Is okay? Everybody okay? All right. So another is a 35. 35. I still have 15 minutes. Okay. All right. So far we talked about the acids and bases. Those are called Bronsted. Those are called Arrhenius definition, given in 1800. There is another definition of acids and bases called conjugate acids and bases. And as you recall, some of the acids that we talked about, they must have a proton, or bases must have a hydroxide ion. There are some bases that don't have neither a proton or hydroxide ion. How to classify them? Based on those, there is another definition that came up. It's called Bronsted-Lowry definition. Bronsted-Lowry definition. Bronsted, right? B-R-O-N sted, S-T-E-A-D, Bronsted-Lowry, L-O-W-R-Y, Bronsted-Lowry definition. So far, we walked to the Arrhenius definition of acids and bases, and we came up with all those things. There's another definition called Bronsted-Lowry definition that gives us the conjugate acids and bases. So that definition gives us the conjugate acids and bases. What are the conjugate acids and bases? So acids with or without proton or protons, and bases with or without hydroxide ion. They could be conjugate acid or base. So basically, they don't need to have the proton or hydroxide ion in order to be base. And one such example, I'm giving you NH3. NH3 is the ammonia. I don't see any proton because these hydrogens are covalently linked to the nitrogen. I don't see any hydroxide ion, but it is a base. Why it is a base? What basically happened, it reacts with H2O. It reacts with H2O, and that will make you like this, NH4 plus and OH minus, ammonium hydroxide. This dissociation is a weak dissociation. It's a reversal sign. So ammonia plus water makes the ammonium plus hydroxide ion. So now we get the hydroxide ion base. So in principle, what is happening, ammonia, NH3, using the lone pair and taking the proton from water, making the ammonium ion, leaving the hydroxide ion. So it is taking the proton and leaving the hydroxide ion. But since it's accepting proton, it's called base. Sodium hydroxide is a base. All right. Likewise, if you take the say HCl, for example, HCl, and if you add some water to it, H2O, right? H2O, and you'll basically end up with H3O positive, and Cl minus. So basically, the water, HCl, water has a lone pair of oxygen that will take the proton from HCl and making the hydronium ion. Of course, HCl we know from the CO that is the acid, but acid is so this is the acid. Then what is this? This is accepting proton, like a sodium ammonia, and water is a base. Water could be acid or base. We talked about, right? So in this case, ammonia plus water is acting like a acid, giving the proton to ammonia. In this case, HCl plus H2O, water is taking the proton from HCl, water acting like a base. That's why water could be acid or base. We talked about. And in this case, these acids and bases, they don't have, especially NH3 doesn't have a proton, but still, or hydroxide ion. Once you dissolve in water, it makes the hydroxide ion. So that's why the Bronsted-Lowry definition of conjugate acids and bases. So what are the conjugate acids? So a conjugate acid that basically donate protons. Remember, no water is not needed. So conjugate acid, the definition of conjugate acid is as follows. Conjugate acid donates proton. Acid donates proton. So acid donates proton. That's a conjugate. That's basically the definition of conjugate acid. So acid donates proton. Bases accept proton. Bases accept proton. And that's basically the definition of a conjugate base. So bases accept proton. And as they accept and do not accept a relationship, they create so let me give you, so they basically they'll create the conjugate acids and bases. Let me give you the example. So weaker the, and there's a principle, the weaker the acid, stronger the conjugate base, and stronger the acid, weaker the conjugate base. So let me go to the next slide, and that will explain the example. So this is the example, all right? So HCl, hydrochloric acid, it's an acid. H2O, water, that is taking the proton and making the Cl minus, chloride and hydronium R. So water accepting the proton from HCl, HCl is donating the proton. So since HCl is donating the proton, it's an acid. Water is accepting the proton, it's a base. When HCl is donating the proton, it is generating a Cl minus. Cl minus is the conjugate base of HCl. Cl minus is the conjugate base of HCl. So the relationship is acid creates the conjugate base. Base creates the conjugate acid. And so water converting into H3O positive, hydronium R, that's a conjugate base of water. Cl minus is coming from the HCl, so there's a conjugate base of HCl. So the relationship is acid gives the conjugate base, base gives the conjugate acid. So that's a pair. They're always a pair. Likewise, another conjugate pair, if you take like this way, so that's acetic acid. It has one proton right here. That's one proton. Ammonia will accept the proton, will become ammonium ion. So ammonia is accepting the proton. It's ammonia is a base, we already know. Base accept proton, and it is converting to ammonium ion. That's a conjugate ammonia, conjugate acid of ammonia. That's a pair. There's another pair, acetic acid is converting to acetate ion, CH3CO minus, giving the proton to the ammonia. So acetate ion is a conjugate base, conjugate acid, conjugate base of acetic acid. So they always pair, always acid-base reaction. So that's acid and base reaction. They always have two pairs. So acetic acid slash acetate ion, acid conjugate base pair. Ammonia base and then NH4 plus is a conjugate base pair. So always acid base. So these are called, there's a concept of acids and bases, and the conjugate acids and bases. And by definition, acids donate proton, base accept proton, proton acceptor. Acid base reaction is always a proton transfer reaction. Remember, there is no water here. And that's basically that's the concept of Bronsted-Lowry definition of acids and bases. Conjugate acid base pair, any pair of molecular ions that can be interconverted by transferring a proton. That's basically, you see it right here. Everybody okay? Is there any question? Is there any question about conjugate acids and bases? Yes? All right. If not, so that's basically, remember, this is a Bronsted-Lowry definition of conjugate acids and bases, and you must remember that. You must remember. Now, let me give you. Okay, let me go to the next slide. Or before I go to the next slide, let me give you an example. So now, if you have an acid, let's say HA, it's a general acid, and if you give the water H2O, and it dissociates like this, H2O, and you have the dissociation like this, reversible reaction, and you get the H3O positive hydronium ion plus A minus. Tell me, can you give me the pair? What's the conjugate? What's the acid conjugate base, base conjugate acid pair? Can you give me the two pairs? Who can give me the two pairs? Yes. So acid plus water make a hydronium ion, is A minus. So what are the pairs? Conjugate acid base pair. Can someone give me? Acid slash conjugate pair. Anyone? Yes. So you have HA, right? Yes, HA is generating A minus. So what's the A minus? HA is the acid, A minus is the conjugate base of an acid. And there's another pair, H2O is a base, and is generating hydronium ion, H3O positive. So the hydronium ion is the conjugate acid of base H2O, and HA or A minus is the conjugate acid of conjugate base of HA. Everybody remember, right? You must remember that, because you have to identify in the test. Usually I ask, I will give you the reaction, for example, like this, and you have to identify the conjugate acid base pair. Remember, conjugate acid is a proton donor, base is a proton acceptor. And when the acid donates the proton, it generates conjugate base. When base accepts proton, it generates conjugate acid. All right? Anyone has a question? Yes? Anyone has a question? No? All right. So now let's we'll go to the next question. Let me give you one more equation, and see how you can do it. So let's say if we'll go to the properties later here. So let's say if we have this molecule H2CO3. What's the name of this molecule? H2CO3. Anyone? What's the name of the H3CO3?
Hydrogen carbonate?
It's a carbonic acid. You can say dihydrogen carbonate. You can say that, but it's a carbonic acid. We talked about it's a weak acid, so it dissociates sparingly, weakly, and it is creating hydronium ion plus HCO3 minus. Now, who can tell me what's the acid conjugate base pair? Give me an acid conjugate base pair for this one. Acid and conjugate base pair.
The HCO3 minus is
So let
the
me write
base pair.
H2. So H2CO3 is the acid, right? Everybody okay? Slash, what's the conjugate base of carbonic acid?
The HCO3 minus.
Yeah, absolutely right. HCO3 minus. So your pair is right here. Yeah, very good. Another pair. There's two pair always. Base conjugate acid.
H2O.
H2O. That's a base. Slash
H3O.
H3O
plus.
positive. Very good. Excellent. Very good. So that's basically you determine the conjugate acid base pair. And you must always remember this. So weaker the acid, stronger the conjugate base. You must remember the principle. It's very, very basic principle of conjugate acids and bases. Weaker the acid, stronger the conjugate base. Stronger the acid, weaker the conjugate base. So let me give you this one. I'm going to give you sulfuric acid, H2SO4. H2SO4, and its conjugate base is SO4 2-. Now, SO4 2- is the conjugate base. Now, SO4 2-, is it a strong conjugate base or weak conjugate base? H2SO4 is acid, conjugate base is sulfate ion, sulfate 2-. The question I'm yes, please.
Conjugate base. H2SO4 is the weak conjugate base.
So H2SO4 is the acid, sulfate ion is the conjugate base. Question is sulfate ion is a stronger conjugate base or weaker conjugate base?
Weaker.
Stronger the acid. Remember, sulfuric acid is stronger acid. We talked about sulfate is the weaker. Excellent. Very good. Absolutely right. So likewise, you can also give like this. So NH3 is the base. And conjugate base and conjugate acid is NH4 plus. Is NH4 plus a strong base, a strong conjugate base, or weak conjugate base? Ammonia by nature is weak base. ammonia is very weak base. So ammonia is a weak base. So NH4 is a strong conjugate base or weak, strong conjugate acid or weak conjugate acid. Yes?
Strong.
Yeah, excellent. So weaker the acid or weaker the base, very similarly, weaker the base, stronger the conjugate acid. Yes, that's right. Absolutely right. So this principle that you have, this for the acids, but you can also apply the same for the base. Stronger the base, weaker the conjugate acid, weaker the base, stronger the conjugate acid. That's right. That's right. Very good. All right. All right. So we'll talk about next time, next Monday, we'll talk about the properties of acids and bases. Properties of acids and bases. I'm not going to start today. All right. Everybody okay? All right. All right. If you have any question, you can stay. You can stay for a while, and then I'm going to entertain your questions. And some of you, I call some of your names, so please stay here, okay? Sabrina Vaughn, you should be there somewhere. And Nicholas Swindle, right? Nicholas, sorry, I didn't spelling right. Yes, I think so. Nicholas Swindle.